Today I'll be presenting interactive streaming infrastructure with JupyterHub and Apache Flink on Kubernetes. So it will be based mainly using just open source tools and how you can actually provision and provide interactive streaming infrastructure to your other end user teams. The main motivation for this talk is streaming is hard, but by building and providing managed and interactive streaming service, you can lower the entrance barrier for streaming and also make adopting streaming at your company easier. I'll share our experience how you can build streaming platform and scale it up based on purely open source technologies. Here's our agenda today. I'll present several challenges for streaming adoption and describe how it can be tackled with potential solutions. I'll describe learning streaming paradigm challenges, infrastructure, and language challenges, and then I'll share potential solutions, how they can be solved, basically. In the second part, we will deep dive into interactive streaming infrastructure on Kubernetes, and first starting with single pod and then scaling it for big data scale. The first one is actually steep learning curve. People have been using batch processing for a long time, but for streaming is relatively new. So they need some time to do the mind shift to understand streaming concepts. They need to differentiate between event time, processing time, or what is watermark, or how to handle late arrival data, or out of order events. So this kind of concepts are new for the people. So solution usually for Solution for alleviating this kind of challenges might be providing lots of examples with FlinkSQL or PyFlink and playground environment where users actually can get hands dirty, where they can just copy, paste the code, and then try it themselves. But the two important things, one is the environment where they can try these things, and then you need to automate and providing them controlled, randomly generated data. Why controlled? Because in streaming, when you need joins, you need to make sure you have joinable data streams, at least two, so they can try different joins and get familiar with APIs. I really like FlinkSQL Cookbook GitHub page by Ververka, which provides small but complete example for almost every feature for FlinkSQL. This way, with a variety of different examples, people can see how it is easy to connect Flink, Kafka on clouds with just using FlinkSQL and PyFlink. The main reason I'm mentioning FlinkSQL and PyFlink, this would be two main components for you to provide interactive streaming infrastructure, or APIs, actually. So the next challenge is actually connect the ecosystem. So I'll mainly touch Kafka and Iceberg connectors. Even when you want to use just Kafka and Iceberg, you still need to touch other distributed systems or even schema registry. Your user needs to understand how the schema evolution works and then how they can evolve their Flink application when the schema has changed. Or the Flink state has its own schema also. So for Kafka connector, users need to know how to handle empty partition, as then by setting idle timeout so the Flink job doesn't stall. Or another challenge for Kafka connector can be how partitions need to be balanced, or what should be an optimal number of partitions per given Kafka topic. For Iceberg connector, which is even more challenging, because you need to figure out where to put the table options right. So it's divided among the code and actually on SQL, where let's say you need to specify hints. And then you need to go to Iceberg open source code base to figure out what are the correct options and then where to specify it so you get actually expected output. So solution for this one is actually you can start contribution to better documentation in open source, especially Iceberg, or extra documentation in your team documentation, or for your company might be helpful. Another potential would be setting good defaults in your SDK, which make your customers' life easier also. So this will save them few common mistakes most of the new starters will make. Let's say they just started consuming from Kafka topic, but one of the partitions is empty. The job will just stall because they didn't turn on idle timeout for their Flink pipeline. But with good defaults already configured in your SDKs, you can save tons of time for your customers. So next challenge is actually Flink is complex distributed engine. So it's way more complicated than, let's say, tuning Apache Spark, where also tuning Apache Flink might be different for depending if your users are using Flink Java or Flink PyFlink or actually FlinkSQL. Because if you scaled it for Flink Java, but if your users started using PyFlink, there's Python process involved. So you need to pay attention, like how much memory to allocate to Python process. So, or for FlinkSQL, where most of the operators are actually dynamically generated. You even don't know which operators or what will be their name, so you can actually set per each individual operator. The only thing you will have is most probably job level parallelism, or only for your source and sink operators, just you can set the parallelism. So it was challenging, and it would usually take 1 or 2 weeks to stabilize large-scale Flink pipeline for an experienced engineer. But this was before Flink Autoscaler was born. So like our teams at Apple have contributed a lot to Flink Kubernetes operator, which has one component, which is Flink Autoscaler. Basically, it can autoscale your pipelines based on the data volume like it gets in the meantime. And the initial version only supported tuning the parallelism of the job, but starting Flink 1.8 version, it also now supports like memory tuning also. It doesn't touch the managed memory, which is usually for RocksDB, but the rest, your pod memory basically for your task managers or job managers can be tuned by Flink Kubernetes operator. It also supports both Kafka and Iceberg connectors now. Now we'll switch to infrastructure challenges, what kind of challenges you can face. So while running Flink pipeline on Kubernetes, either your GM or like job manager or task manager might restart due to various reasons. It might be due to unhealthy node on your cloud provider, and then, or it might be due to cluster maintenance performed by your DevOps teams. And then depending on your job graph, different kind of restarts might cause the whole job actually to restart. Then here's a potential solution would be again Flink Kubernetes operator, which helps you to overcome this challenge. So you just need to enable HA mode for your job managers, and then for task managers, a Kubernetes operator will handle it out of box. It would be just pod failure, and it doesn't need to, if you set like your partition policy correctly for your Flink job restart, then it will only cause partial of your graph, assuming your graph is not like connected graph for your Flink, then it will cause only for your partial job restarts, and then the job will continue. So you don't need manual intervention for that. Another challenge is actually related to, let's say you're running on public clouds and you're running really large scale Flink job. You might need to scale multiple components in addition to Flink itself. Like one of the main common issues might be hitting put limits of object storage for different like cloud service providers, either for your Iceberg tables, if you're using Iceberg as a sink, or for your checkpoint buckets for Flink job parallelism. We are talking here about like few hundred or like even thousands parallelism for single operator for your Flink pipeline. The solution for this would be you need to enable entropy for your Flink pipeline, and also you need to work actually with object storage service providers. So you manually request extra partitioning on your bucket. You need to provide them how your data will be ingested, and then where the entropy hash need to be injected in the path. Let's say if it is a S3 bucket, like where they need extra partitioning so you don't get hit by put limits. Again, it might be at two places, both for checkpoint, which is for Flink's own resilience, and then it might be also for your Iceberg tables where you ingest the data. Another challenge is, while running on a big data application, having great monitoring dashboard is one of the major requirements. So you can constantly monitor the cluster cost, cluster utilization, both CPU and memory-wise. But again, like running Flink on clouds, usually Kafka as a streaming source. Like the main two connectors we use are Kafka or Iceberg. And if you use Kafka as a streaming source, it requires the user to understand how cloud providers charge for their services. For example, if you collocate your Kafka cluster and Flink cluster in the same availability zone, it might help you to save huge network costs. Now we'll talk about language challenges. And here we are talking about programming languages used by different user categories, basically. So when we started, we targeted mainly big data engineers for building like our streaming platform, and we mainly like tried to acquire those big data engineers who have like really good Java experience. So, but once you build your streaming platform, you need to grow your customer segment basically, and then you need to get machine learning or data scientists also. But those engineers are usually not Java friendly. They would know Python well, or only let's say or Scala sometimes, but mainly either Python or SQL. So this kind of organic requirement pushes the infrastructure team to provide Flink's 3 APIs, like Java, PyFlink, and FlinkSQL, to satisfy the needs of all the customer teams. So Flink has a layered API with FlinkSQL and PyFlink at the top. For streaming analytics and ML, we suggest using SQL and PyFlink to our customers, and due to their user-friendly nature, while maintaining expressive capabilities. But on our platform, users can opt for Java API also for greater flexibility and power, but with added complexity. Like even though Flink provides all these 3 APIs, but the most feature-rich API is the Java API still. So some features are still lacking in PyFlink or FlinkSQL, but it adds extra complexity. They need to know like Java. So FlinkSQL is the easiest API for building streaming apps, and it is because it is declarative and it implements ANSYS SQL standard. SQL also is the most popular language among machine learning people and also like data scientists. So by just writing SQL statements, Flink allows you to utilize the power of Flink's horizontally scalable stream processing engine without the requirement of being like Java or Scala developer. FlinkSQL makes it possible to easily tap into large volumes of raw in-flight data and facilitate creation of custom tables and dashboards in a self-service manner. Like user can define their UDFs in Java or Scala if they want to, or just Python. So depending on the use case, FlinkSQL plus Python UDFs might be good enough to solve like most of the customer requirements. PyFlink, this is a good fit for ML framework integrations, such as like if you have, let's say, real-time inference on top of your streaming pipeline, and then you want to use PyTorch for inference, then it might be good to use PyFlink so you don't lose in latency or quality of the model while you do translation between different like model representations. So you can just use natively, let's say, PyTorch. And then this gives you also another flexibility to run on top of GPUs and get benefits of like NVIDIA GPUs and like easy integration actually. Then PyFlink supports both table and data stream APIs, also simplifies pipeline testing. Like one of the main headaches of FlinkSQL, it's very easy to get started to write your pipelines, but it's very hard to test because you only have the input control and you know kind of what is expected output, but it's very hard to test FlinkSQL itself. But PyFlink makes it way easier. So its integration with Python, which is a popular language in data science and ML, extends Flink's reach to ML users. Additionally, like PyFlink accommodates Pandas, which is widely used Python model. So before moving, actually, these two, both FlinkSQL and PyFlink in open source community is kind of underdeveloped compared to Java. So it's also a good opportunity for developers if you want to become, let's say, Flink committer, then just to focus on like adding or moving like existing features from Java API to PyFlink, or like more contributing in these two areas. So the next, we will talk about interactive streaming and development. Just one thing to make clear, this one is mainly for development workflows. This is not for production, running. Let's say this will help you to build the right pipeline for yourself, but we don't recommend running it in this way for production. So you build it and then you can easily migrate it, take your scripts, either PyFlink, basically Python script, or if it is FlinkSQL, and then run it in production, basically. So far I have presented challenges, but the goal is not to scare you. So now I'll talk how we enabled interactive streaming development. First, we'll start with single pod use cases, and we believe managed service and interactive service makes adoption of streaming easier. So Flink open source comes with FlinkSQL client, which is kind of the main entrance for using FlinkSQL. And then Python users are already used to IPython notebooks. So we continued using these two means for building interactive streaming on top. So we were looking for a way to put this FlinkSQL client into a basically shell, and we wanted this shell to run on clouds, so all the users can access this one and start writing FlinkSQL code. So we didn't want for the user to set up any infrastructure or anything to get started. So they just needed the web browser and then internet access to get started. So luckily, our sister team was already providing JupyterHub on Kubernetes as a service, so we decided just to reuse it also. Basically, they can just go and create multiple sessions on JupyterHub, and most of the people were already familiar with JupyterHub Workspace UI, and then notebooks, and then terminal. So how to start FlinkSQL client is just single command line. So next, we basically took the Jupyter Lab image and then extended it with adding Flink on top of it. So when Jupyter Lab image is started for the user, this image will be running several components in it, like FlinkSQL client, Flink cluster. And the user notebooks and code files will be persisted in EBS because you don't want the user data or whatever user code they wrote, like FlinkSQL or PyFlink, to be erased whenever their notebook is shut down. Usually it will be shut down after a few hours of inactivity. So, but if you store it in EBS volume on Kubernetes, then it will be persisted across Jupyter Lab runs. With single pod design was good enough to be used by users when we started, as Flink is not as memory hungry as Apache Spark actually. But as you know, soon we hit the limits. So single pod resources are limited both in CPU and memory. So, and then we had local Flink clusters just running on single pod where you have very limited resources, like how many task managers you can start or how many task slots you can have in that local Flink cluster. So your basically Flink cluster is capped both in size, in TM count, and also how many task slots. This becomes challenging, especially when the user uses IceBag connector. If input table is really huge, then let's say several terabytes, then you face this challenge. Flink's job manager's memory is kind of directly dependent on table size, input table size. So larger your table, more memory you need to grant for your job manager, basically. So for streaming ML use cases, users also might need to run TMs on GPU-enabled pods, but with this kind of single pod setup, where usually JupyterHub infrastructure will not run on GPU pods or GPU nodes, so we will not be able to get any GPUs. That's why we basically switched to more at scale running it on Kubernetes. So we moved away from single pod way running. So now I'll present two ways for interactive streaming infra. One is FlinkSQL, another one is PyFlink. So first we'll start about FlinkSQL at big data scale. This is, on the screen you see, we have the SQL client. It might run on a separate EKS cluster, basically. And then we have other two EKS clusters. So on one of these EKS clusters, you see the control plane, which we can simplify it as a kind of web service, basically, a web server, which also has proxy servlet in it. I'll describe why proxy servlet is needed there. But when a user basically submits SQL to So actually, the first step is starting the session cluster. So a user will submit creating the session cluster in Kubernetes. And they need to be intra-cluster and connection between where your control plane is deployed and actually on the second cluster where your Flink Kubernetes operator is running. So Flink Kubernetes operator is the one which starts your job manager and task manager pods basically and handles any restarts or any failures. So that intra-cluster communication is needed between your control plane EKS cluster and your Flink Kubernetes operator EKS cluster, basically. So the first thing, once the user submits creating session cluster, your control plane will send as a CR custom resource to Flink Kubernetes operator, which will then start a SQL preview cluster, which is like session cluster. And then you can see SQL gateway. We modified the Flink image to actually start SQL gateway as another process within the job manager. But if you get lots of traffic, then you can run it as a side container also, basically. Then control plane takes care of provisioning the connectivity layer by setting up the corresponding service and ingress components. Like we don't expose the ingress globally, but instead generate a control plane endpoint and relay requests using the proxy servlet. So this allows us also to apply like OSN or OSZ on the control plane side. So before even the job is like created or the session cluster is created, we can apply the same like authentication or authorization like on control plane. So this is like going with a proxy allows to enforce like the use of standard OSZ OSN, which is already implemented in control plane. And after getting the URL of your session cluster, when you start your FlinkSQL client, you can just specify this URL that, okay, this is my SQL gateway endpoint. And then users just connect to that remotely running SQL gateway. And then the model with session cluster make it possible to easily scale to large preview jobs using all available like cluster resources. And Flink Kubernetes operator actually supports scaling up session clusters also. So like if that session cluster is small, then Flink Kubernetes operator can scale it up, like to have very many, like more task managers or increase, let's say, bump up the memory or parallelism depending on the pipelines running there. Now we'll switch gears to PyFlink, basically how you can provide PyFlink as an interactive development workflow, basically, on top of Kubernetes. Again, the first thing, you go to JupyterHub and then you open the terminal this time, and then you submit deploy JSONnet. What this deploy JSONnet is, basically you define your Flink job or your any configurations, like how much memory you want to give, how many like CPUs you want to provide, or any arguments you want to pass, or if you want to provide GPU resources, or like any of this kind of requirements you specify in your deploy.jsonnet file. Then control plane will authenticate and also authorize that the user has access to run jobs in the given namespace. So the infrastructure is it's almost exactly the same actually. We have exact same control plane for both PyFlink and FlinkSQL, and we use exact same JupyterHub actually. Then control plane will submit the CRD to Flink Kubernetes operator to start job manager and task manager like of session clusters. So in this way, basically, user have submitted creating session cluster to control plane, which is running on separate EKS cluster, and then that one routes it to Flink Kubernetes operator, which will start, it can be like start jobs in multiple different namespaces, and then it will start job manager and task managers based on what you specified in your deployment JSONnet, basically. At step 2, once your session cluster is up and running, basically user can write PyFlink jobs in IPython notebook. Like this is no different than, let's say, writing any IPython notebook. You just import in your requirements. We already built like a PyFlink as dependency, so it already comes shipped with the image. So you can just start writing like PyFlink pipelines and like start importing it. When the cell is executed this time, let's say you wrote your PyFlink job and then you execute the cell, the Python code is automatically converted into a Flink job graph in the background. So the job graph is submitted to control plane, and then control plane will authenticate and authorize the user. So the difference between PyFlink and FlinkSQL, FlinkSQL, the actual SQL code is getting submitted to FlinkSQL gateway. That one generates the job graph and then sends job graph to job manager. But in this case, the job graph creation is done on the Jupyter side, like on Python notebook. We are this PyFlink SDK basically. Once a user is authenticated and authorized to run this pipeline at that specified namespace on Kubernetes, then the control plane will submit the job graph to job manager of session cluster, and then the user job basically will start running. And this might be, let's say, you do some, let's say, select queries from your iceberg table, like in a streaming way, or from your Kafka topic. Then the results, the output is transferred back to IPython notebook cell output. So you don't need to leave this notebook ecosystem. So you will start getting the results back and actually visualized on your notebook, basically. That is the end of my presentation. I'll be glad to answer any questions you have now.